morning, everyone. Thanks for coming here and listening to this final project presentation. This is the final project presentation for the TR-738. This project was on the investigation of the effects of shrinkage and temperature forces in frame Piers, and that's the project that we did at Piers State University in collaboration with HTR. So I wanted to acknowledge the contribution of my colleague Al Nelson, who wasn't able to join today from Nebraska, but he did help us with this project and some of the activities that we had. I'll talk about the details in more detail. The outline of presentation for today, I'll start with a brief introduction, the bridge inspection activities that we had, field instrumentation with big instrument, 2 bridges as part of this research project, modeling shrinkage and creep, finite element model development, parametric studies, and then a set of comparisons with linear models, just to be able to see how the current design guidelines are compared to more sophisticated, more complex analysis. And I'll end with a set of conclusions. We covered a number of topics in this research project, but given the time here, I'll be brief. And starting with the need statement, frame Piers, we have seen them in several instances in bridge structures. They offer essentially an economic and viable choice of piers in bridge structures that included other alternatives in this slide. It helps us save these materials while providing superior structural performance. But the key question is how wide they can get and how we can capture the forces associated with this type of frame. And I have included a few examples of them. So the key question for us, which also defined the objectives of this research project, was to obtain detailed information about the structural performance of these piers. And there are simplified analysis stage, but they don't capture various factors, especially in terms of how time-dependent temperature effects, shrinkage, and creep would influence the response. And as a result of that simplification, what we noticed that increased the level of force considered for the design, and that unavoidably led to larger structural elements and continued all the way to the foundation system, so larger foundation size, and sometimes requiring to include an extra joint to be able to accommodate those expansions and contractions in the frame pier. So that can result in settings like what I have included in this slide, which is less than desirable in terms of aesthetic, and more importantly, we require additional form work, construction activities that will add to the time and cost and labor required for the project. So the main research objective first was to understand the structural behavior of frame piers, and the focus was to understand the effect of temperature and shrinkage. We also included the effect of creep. That was not outlined in the project title, but that was one of the time-dependent effects that we normally consider when we are dealing with concrete materials. And then based on that, quantify the forces frame piers experience due to these effects, and also be able to evaluate the vulnerability of existing ones, identify the most influential parameters, design factors for this category of piers, and then evaluate how the simplified design procedures that we have in place, how they are compared with what we obtained from the field, and more detailed finite element information. So as part of this research project, we first of all visited a total of 10 bridges, 9 or 10 bridges, and those were bridges essentially selected based on an initial susceptibility metric that we had, and that was based. We don't have a rich literature on this topic, and the initial perception is that the ratio of the total width to the height of the column would be the main governing factor or the main point for us to consider in terms of design. And for our bridge inspection activities, we consider the range, so essentially cover different stages, foundation type, skewness angle, and here you can see the result. You can see the list. The result was essentially no notable damage we observed. Of course, we couldn't reach the foundation or observe what happened or what could have happened to the foundation. But the connection between the column and the foundation, the length of the column, and also the cavity, there were no signs of damage or deterioration that can be associated with various issues. A common sign of damage, like cracking the concrete, is quite common, but no signs of damage that could be affiliated with temperature and shrinkage effect. And that was essentially our initial conclusion that those spring piers are not under design in I1. So we went further. We selected, in collaboration with the project technical advisory committee, 2 spring piers. One was 418 Woodbury, Sioux City, and the length of the casting was 56, close to 56 feet, column height 15 feet and 6 inches. So we instrumented this spring pier. Essentially, we focused on one half of that because of the symmetry, and we placed a total of 26 strain gauges for us to be able to monitor the strain development, and those strain gauges are able to also record temperature, so we can obtain a good correlation between temperature, the strain, and with material properties. We can move that further to the stress effect. So we visited those 2 bridges frequently during the time of construction. We take the gauges before the concrete was poured so that we can monitor how the strains are developed. And here you can see our data collection unit and solar panel in place so that we started collecting data from this spring pier. And here you can see the trending temperature. And the interesting point with this plot is, as you can see in the initial stages, initial days, we essentially have like those higher temperatures inside the spring pier, and that was associated with the heat of hydration, the heat produced as a result of the hydration reactions that happen in concrete. And then we started observing those fluctuations in temperature based on the ambient temperature capturing hot and cold seasons. And that led to the strain data that we recorded over time. As I mentioned, we had a total of 26 strain gauges. And with that, we essentially noted that if we go back a bit on this slide, so essentially at the connection between the cap beam and the column, looking at this, like the strain gauges G7 and G8, and also looking at the base of the column, G1 and G2, were the places that we got the most demand in terms of the strain and stress. So that was the initial observation that we had from this spring pier. Then we continued with another spring pier, and that spring pier was more susceptible to effects of temperature and shrinkage. That was because it has a wider length, shorter column, and based on the initial susceptibility metric that we had, it was more prone to the effects of temperature, creep, and shrinkage. The second bridge was located in Davenport. Again, we visited that bridge frequently to be able to place the gauges at the time of construction. And here, again, we focused on the last 2 columns. We know that the demand on those 2 last columns is the highest, so we focused on those 2 last columns, and again, utilized a total of 26 the strain gauges, recording temperature and strain, and the profiles were obtained and processed. In brief, in terms of the outcome, the main findings were that the columns in general appear to be more susceptible or sensitive to the effect of temperature and shrinkage compared to the cap beam, especially the top portion of the column. And exterior face of the base of the outer column and the interior face of the top of the outermost columns are those regions that are more susceptible to cracks. But from the inspections that we had on those two instrumented frame piers, we didn't observe any signs of crack or damage during the 3-year duration of this research project. So they had satisfactory performance. So we moved ahead. We know that with field instrumentation, we can only capture so many parameters and effects. So we moved forward and started modeling the shrinkage and creep. We utilized the database. The database is publicly available. It's essentially a collection of various shrinkage and creep experiments. And we utilized the ACI 209 model to be able to model the creep and shrinkage effects, and then utilize those models within our finite element program. We utilized Abacus, and we modeled the entire frame pier, and we included the rotational stiffness at the base of the columns following the Iowa DOT bridge design manual, just to be able to capture the foundation effects. And here you can see how the finite element model, the base model, looks like. Essentially, we captured the effects of beams on top of the cap beam through the dead load and live load applied to them. Rebars were explicitly modeled, and we did, of course, mesh sensitivity analysis to make sure that the results make sense and are accurate enough. The thing is that Abacus cannot directly incorporate the effects of shrinkage and creep, so we prepared a separate subroutine utilizing the Fortran language. I know Fortran is getting like sort of outdated in the research domain, but still Abacus works based on a Fortran-based like subroutine. So we developed that so that we can take into account the time-dependent effects. Essentially, we updated the material properties in time steps so that we can like really analyze, understand the strain and the stress development. And based on what we obtained, we did a validation study just to make sure that what we obtained from the finite element model is accurate enough, meets like what we observed in the field. Again, in terms of temperature, you can see how the results between the finite element model and the field are compared. And with capturing the temperature, we also made comparisons on strain and stresses. After model validation, we moved forward and considered the parameters of strain. Those are the design parameters that need to be taken into consideration, and some of them construction parameters in terms of time of casting and some of the detailing. So the goal was to identify factors that most influence the structural behavior of frame piers. And we looked at the time of casting, column stiffness, considering different stiffness parameters, uniform and non-uniform distribution, bay length and frame length. So here you can see the variations that we considered, for example, for uniform column cases. So we considered different heights. We were also interested in knowing what the contribution of the column section dimension is, and that is often captured with the moment of inertia of the section. So we also considered that as a variation. And as you can see, like column height is what we found is more significant than column width. And when you're comparing different response measures like shear and moment, we can directly observe that the column height has more influence on the overall structural behavior. We pushed this one step further, so we looked at the crack development. That's something that in the field normally cannot be captured by just direct, simple visual inspection. So as you can see, those are the focal points are the regions that we identified as the points where cracks start forming. Again, cracks are minor, not like sort of major, like spalling or collapse. But as you can see, what we obtained from the finite element model was very much consistent and supportive of what we observed in the field from the recorded data, because our recorded data from those G7 and G8 sensors and G1 and G2 sensors, they were also indicative of those like potentially susceptible regions. We also took a look at the non-uniform column cases for exterior columns and also a variation in the column properties. There are situations that we cannot be consistent in terms of column dimensions or sections throughout the entire frame pier. But what we found is the effect of those variations essentially are like minor. The change is like really in the range of 3 to 5%, not comparable to the main like sort of effects of column height and also the width of the frame pier. We looked at the frame lengths, and based on that, like we essentially compiled all the observations, and we looked at what we call the susceptibility metric. And if you look at the frame lengths alone, what we observe is essentially somehow of like dispersed like data points. If we can take a look at the length to height ratio, and that's the parameter that is commonly considered in the practice, you start seeing a trend, but again, there are some dispersion included. So one step further that we were able to like identify through this research project was to directly include the stiffness of the column. We look at the E, modulus of elasticity, we look at moment of inertia and height, and based on that we can formulate a stiffness factor, and that is what or how that factor is related to predicting the shear force. And one step further, and that was essentially one of the main outcomes of this research project, was if we also take into consideration the effects of the fixity or constraint provided by the bridge superstructure or by the cap beam, we can also further refine that equation or that predictive model in a sense that we can have a much better prediction about the overall performance of frame piers. So with that, I'm going to just list some of the main like conclusions and findings that we had through this research project. So inspection results showed that the current frame pier design is adequate in terms of resisting temperature shrinkage effects. And field instrumentation helped us obtain actual structural response measures in 2 like real world frame piers in the state of Iowa. And overall, we found that columns are more susceptible than the cap beam. And the exterior face of column bases and the interior face of the column tops, if we wanted to focus further, would be the points that we need to further focus. And based on what we obtained from the field, we were able to validate, calibrate our finite element model so that we could do additional investigations on various parameters. Among those parameters, column stiffness was identified as the most influential factor, and decreasing the column height generally resulted in higher increase in the demand in this type of pier system compared to the frame length. And restraint condition, that was a key aspect that had not been included. We added that to
our like sort of framework to assess these frame piers, and non-uniform columns, day lengths, they had essentially little to no influence. And our final recommendation was to account for column stiffness, cap beam length, and restraint condition. And the outcome of the project led to essentially a set of design recommendations and comparison between what we obtained from our nonlinear finite element analysis with linear analysis. Those linear analyses were conducted by HDR following the state of the practice, and then we made comparisons, and that led to the recommendations that I just mentioned. So with that, I'd like to acknowledge the support of Iowa Research Board, Iowa Department of Transportation. Mike Knopp was the project champion and the project lead on this project, so I would like to acknowledge his time and effort, and also the support of the rest of the TAC members that we had for the project.